In this lecture, we look into how we can reduce the excess P in soils through amendment additions. When we add or when there is an excess of phosphorus in soils, it is going to affect your water quality. So it should be possible to reduce the P loss from a soil by the addition of amendments. And here we will look at two particular amendments, the water treatment residuals as well as the biochar, which you have heard quite a bit of in previous lectures. To begin with, we note that the different P sources have different P solubility, even when labeled as manure or biosolids. Note that when we talked about manure, it could be beef manure, dairy manure, poultry manure, or swine manure, and so on and so forth, and all of them could have different P solubilities. Then we come to biosolids. We have seen that biosolids are very different. They have different P solubilities depending on how they were prepared. And we also noted that consequent to these applications, at the same total P levels, the P loss from the soil and its effect on water quality depends on the source of the P applied. Now, the soil that was selected for this study to test out the amendment and what it can do to retain P was the surface soil of a democally fine sand, which has minimal P retention. As we well know, soils vary in their ability to retain and release P, and this was discussed in detail in Module 2. Let us look into the use of water treatment residuals as a soil amendment. What are water treatment residues? Well known or better known or equally well known as WTRs. These are the residues removed from water supplies during the preparation of drinking water. See, the water is treated with a coagulant, usually aluminum, iron, or calcium, and the residue is a mixture of clay, silt, some organic matter, and of course the coagulant. And when the coagulant is aluminum, it is normally referred to as aluminum water treatment residue. Application of water treatment residuals. You will see the picture on the left is collecting WTR that is left after the water treatment, and on the right is the land application of the WTR. Question then is, why use water treatment residuals as soil amendments? See, water treatment residuals could be a viable choice as an amendment since they are easily obtained products from water treatment plants and are available at no cost. All right? And as I've mentioned earlier, WTRs may be aluminum, iron, or calcium based. We can also use other chemical amendments to increase the P retention and reduce the edge of field losses. We will now demonstrate the use of the water treatment residue. We will use the rainfall simulation technique as you have seen earlier. What we are looking at here is various aluminum water treatments, and details will be given in a little while. And we can monitor both runoff and subsurface flow, and they can be collected from the various treatments. Here is an example of how the whole setup looks. You have surface runoff, subsurface flow, and you could have some forages or grasses that are grown too. So this is the setup of the rainfall simulation with different amounts of WTR. Now, let us look at the water-soluble P in the runoff. C1 says no water treatment, residual. and you have a 0 to 10 and 10 to 20 centimeter soil layers. Treatment 1 is WTR, surface applied, again the same depth. Treatment 2, T2, is WTR, mixed in the 0 to 10 centimeter soil layer only. Treatment 3 is WTR incorporated with 0 to 10 centimeters and 10 to 20 centimeter soil layers mixed together. And C2 is another control, but this time no WTR, but 0 to 10 centimeter and 10 to 20 centimeter soil layers mixed together. Now this is, you will recall that in the earlier rainfall simulation experiment, we used boxes that were 20 centimeters. At that time we subdivided in smaller increments, so 5 centimeter increments or so. Here there are only 2 increments, 0 to 10 and 10 to 20. If you look at the water-soluble P in the runoff, you will notice that the water-soluble water treatment residuals reduce the P that is collected in the runoff. That is, there is less P in the runoff compared to a soil without treatment, that is, compared to a control. Both the first and the last bars are controls. The details are provided in the box to your left. Now let us come back to the SPSC equation. Remember, this is one of the new techniques, and we are trying to go back and look into how the technique can be used. We know the SPSC equation for surface horizons. It's simply a difference between the threshold PSR of 0.1 and the PSR of the soil multiplied by oxalate iron plus aluminum expressed in moles and multiplied by 31 to bring the value of SPSC to milligrams P per kilogram of soil. And we also mentioned that the SPSC can be calculated using Mehlich 1 or Mehlich 3. The Mehlich 3 is supposed to simulate very similar to that of the oxalate, so the equation is similar to that of the oxalate. The equation can be rearranged as SPSC with 0.1 molar iron plus aluminum minus P and multiplied by 31. Now we look into SPSC and water treatment additions. Water treatment additions can be adjusted to give 0 SPSC or SPSC to a desired level. Controlled application has got both agronomic and environmental benefits. If you look at the figure, the top figure is a glasshouse study, and the second figure is a field study. In the figure to the top, you have SPSC, which is both positive, that's to the left, and negative, that's to the right, ranging from 0 to negative 250 and positive 200. And the y-axis is the soil water extractable P. Now, if you look at it very carefully, you have treatments with different amounts of WTR. 0 WTR will of course be the control, 10 grams per kilogram of WTR and 25 grams per kilogram WTR. What you notice, of course, is that the more WTR is added, the more positive the SPSC appears to be. And if you say at just 10 gram per kilogram, you may still have some negative SPSC. Now this depends exactly or entirely on what the SPSC level you need. If you add too much of WTR, you probably go into the positive side of SPSC, and you may not be able to have any plant growth, because plants, of course, need phosphorus. Now look at the field study to the bottom figure here. There are 2 different types of field studies at 2 different times with it's actually 3 different times, with and without water treatment residue. The open circles are the ones without water treatment residues, and the closed ones are with water treatment residue. It's pretty obvious that the ones with WTR moves to the left. That means we are looking at positive SPSC, and the one to the right is the open squares, that is without water treatment residues, are mostly on the right side, which shows that it is negative. That is, the soil is negative prior to the addition of water treatment residues, and positive when WTR is added. This is a field study, and therefore it simply shows that when you add again WTR out in the field, the likelihood of the SPSC being converted from negative to positive is pretty high. There is one thing we need to remember at this point, is that this is a one-time experiment. We do not have additional information on what to happen if the WTR is left there for a long period of time. There are always glitches which we may not be able to foretell up front, so we need to look into some of these things in a little bit more detail. Now, we have already talked about this a number of times, that is, biochar as a soil amendment. You would realize that we noted that it doesn't matter what your biochar source is, the P is released at a particular SPSC value corresponding to the PSR of the soil. That's calculated from the PSR of the soil. And the more retentive the soil is, the more biochar can be added, because the labile part of the biochar will be absorbed by the soil. Here, biochar additions have been shown to increase the maximum P retention capacity of the soil. That is, if we look at it, the more biochar that is added, the more P is retained. The Smax just increases. We have talked about this earlier. But at the same time, the Smax that has increased may not be stable. Remember, at this point, these are preliminary results, and again, much more work needs to be done on this. But what it does show is that it holds on to more P. Now we come to a different sort of a situation. If a soil is already P impacted, what would happen when you add biochar to the soil? Now, the picture, or the graph to the bottom graph just shows that in a heavy P impacted soil, when you add biochar, the level of P would actually be less. All right. So what does this mean? That is now that the biochar is able to absorb onto the P. But remember, we come back to the same situation, that the one that is adsorbed could be released. This is again very, very preliminary experiment, that the biochar considerably reduced the P in the impacted soil. That is a fact. But how beneficial it is to the environment is something that needs far more studies. If we leave this as it is with biochar additions and come back several months or several years from now, what actually happens to the phosphorus? That's an issue that we have to deal with. Here are a couple of references that we have that are directly related to what we have discussed just now.